and then derived quantities which are predicted from the measurement of primary quantities um, using some formula or relation. Then depending on what we measure, we said that you can have intrusive measurement, you can have non-intrusive methods. Intrusive methods are those where you put in an instrument to measure something, but in the process of measuring, you also perturb the original measurement field. So you need to know how much you need to correct it for what you measure your data, if that is something that is systematic. But non-intrusive, typically the perturbation that you introduce into the field by putting in the instrument is negligible. So you may not need any correction in that case. Right. So that's a brief introduction. Today we would start by talking about a general measurement system. That is, what are the different components of a general measurement system? So we talk about general measurement system. Typically, in a measurement system, of course, you are measuring some variable, some quantity. So you have typically a process input, right? Let's say you are measuring temperature, then the surface whose temperature you are trying to measure, that um, surface temperature becomes the input, right? So you basically have a process input. So this is basically talking about the measured quantity. So in this case, the measured quantity is, let's say, temperature. So the first component of the measurement system will be the sensor stage. When you put in a thermocouple, the tip of the thermocouple basically indicates the sensor. Okay, so this is called the sensor stage, which is the sensor stage is basically exposed to the environment that you are trying to measure. Let's say you are trying to measure the temperature of a surface. The thermocouple tip is exposed to the surface, right? So from the sensor, it goes to transducer. Transducer. What is a transducer? The transducer basically converts one form of energy into another form of energy. Okay? So the transducer stage, in the case of a thermocouple, it takes heat as the input, right, and convert this into electrical signal. So we will be talking about temperature measurement, where we will be discussing how thermocouples work. It is based on an effect called Seebeck effect. So basically, when you have a temperature difference across two dissimilar metals, you induce an EMF, right? And the consequence is some kind of a current. So your temperature difference is converted into an electrical signal. Okay, so and that is done by the transducer stage. Then from the transducer stage, the next stage is called the signal conditioning stage. Okay, so from the transducer stage, you go to the signal conditioning stage. The signal conditioning stage will have the subcomponents. So I'm just drawing it with dotted line. So this is your signal conditioning stage. So what do you do in signal conditioning? You can do, for example, amplification of the data, right? If your data that you measure is very small, let's say you are looking at a very minute difference in temperature and the current or the corresponding EMF that you get is very, very low. So typically you use amplification, right? So you use an amplifier. So you use amplification of the data. You can um, sometimes use a noise filter, right? You can use noise filtration. Let's say you are trying to measure temperature of a surface which is vibrating, let's say. So when it is vibrating, you get a lot of noise in the data because in the thermocouple um, is making a physical contact with the surface, but the vibration can affect the measurement, right? And because of which the temperature is not, let's say the temperature is 50 degrees, it's not really reading constant value, and it is sort of varying between, let's say, 45 degree to 55 degree. Of course, there is going to be some inbuilt tolerance in the measurement, but when you have noise, it actually exceeds the tolerance limit, and you have to get a filter. You have to put an upper limit and lower limit to actually filter the noise. So you need to have a noise filter, and then you may also have some kind of the analog digital converter. Okay, a general measurement system may have these different subcomponent AD converter. In some system, you may have all of these. In some system, you may have just one of these. But these are some generic components, subsystems in the signal conditioning stage. Now, from the signal conditioning stage, next it goes to the output stage. It goes to the output stage where your data is basically displayed in a screen, right? This is basically displayed. And in some measurement system, the output that comes out after signal conditioning is used as the feedback uh, for the sensor stage. That means you may have a feedback control stage. So that the output signal is taken to the feedback control stage, and the signal from the feedback control is fed into the sensor stage. So this is the control signal. For example, let's say you are measuring temperature inside a oven, right? And you have set the temperature of the oven to be 80 degrees centigrade. So the sensor basically, reads the initial temperature inside the surface. Let's say it's ambient. Then it signals the heater uh, for doing the electrical heating, and the temperature slowly rises from 25 degrees centigrade to 30 degree, 70 degree. And then at some point you would see that the way these thermal ovens work, it would slightly exceed the set temperature. Let's say you have set at 80 degrees centigrade, it would go and exceed 80 degree, it will go to 85 degree, and then when it goes to 85 degrees centigrade, then your feedback control stage should tell the heater that it should set a control signal that switch off the heater. So then the temperature goes down, let's say to 75, then it comes back to 82, then goes down to 78 and oscillates, and finally it reaches 80 degrees, right? So that is a typical system that what you see, right? If you have set at 80 degrees centigrade, the temperature basically shoots up and then it slowly oscillates and then finally reaches 80 degrees centigrade. So to achieve these kind of processes, you must need a control signal. Okay, sort of you can control what kind of input is coming to the process environment, so that the environment is controlled, or your process is controlled. Okay, so this is basically a general measurement system. You'll have a sensor, you have a transducer, you have a signal conditioner, then you have output, and you have a feedback control stage sending the control signal. So I will take an example of a slightly a sort of advanced system to demonstrate these different stages. Maybe we can first talk about a simpler a system. Maybe we talk about this oven that I was talking about first before I go to a slightly more complicated system. So in a oven, basically you have a heater. So this heater basically heats the environment inside and controls the temperature. Let's say you have set some temperature 70 degrees, right? This is the set temperature, and you are having a thermocouple inside, and this thermocouple is basically measuring the temperature. And so in this case, um, this inside the oven becomes basically the process input. The temperature, the set temperature basically becomes the process input, and the thermocouple basically acts as the sensor, and the thermocouple with the external circuit uh, act as the transistor, thermocouple plus the electrical circuit, because you need to have a circuit to record the EMF that develops when you have a temperature difference between the hot end and there will be a cold end somewhere. And so basically the circuit with the thermocouple together, they will form the transducer stage. And so you have a signal, right, electrical signal, which is calibrated against the temperature, right? And let's say, as I said, you have set a 70 degree, and when it reaches 75 degree, then you must have a signal conditioning or control stage. Uh, Depending on the temperature, let's say initially it is 25 degree and then it reaches 75 degrees centigrade, then the signal should fed back to this heater, right? It says cut off because the temperature has exceeded the set temperature, right? And so the heater is cut off. So from 75 it goes to let's say 68, and then it comes back to 72, and finally it reaches 70, right? So this is a very simple measurement uh, system where we have the sensor, transducer, you have the signal, control signal stage, and also you have the feedback stage. One of the simplest measurement system you can talk about is like a thermometer, right? So in a typical thermometer, what do you have? You basically have a bulb, and you have a long stem. So inside the bulb, you have and inside this you have mercury, right? So here, this bulb is basically the process space, and here you have mercury, right? And that is basically your sensor. Okay, this is some temperature of the ambient it is trying to sense. So this heat from the ambient gets into this bulb and to the mercury, which basically senses the temperature. And the stem, uh, what happens really when this mercury receives heat, it basically expands. And this expansion, the volume expansion of mercury is converted into linear expansion in this capillary, right? So this mercury along with this capillary forms the transducer states, right? And so basically the capillary plus the mercury uh, together becomes the transducer. And here, once the mercury expands through the capillary, then you have these scales, right, which measure the temperature, right? This temperature scale. The temperature scale is basically the output state. Okay, so you don't have any feedback system here. You don't have any control uh, signal conditioning stage here. You have sensor stage, you have transducer stage, and you have output stage in case of a simple system like a thermometer, right? So now we talk about a slightly advanced system, uh, which is called atomic force microscope. Microscope. So one of the applications of atomic force microscope or AFM is to measure the surface topology, right? Let's say if you have a surface, let's say this is the substrate, and on top you have a surface which is highly irregular. Okay. So one of the application of AFM is to sort of measure the surface topology, how the surface looks like, right? So typically in an AFM, you have a AFM tip, atomic force microscope tip. It is typically pointed, and then it is mounted to a cantilever sort of structure, and which is the other side mounted onto a frame. Okay. And this is mounted onto what is called a G scanner. It basically um, runs over this rough surface and reproduces the topology. So what is important is um, this cantilever tip. Okay. So the purpose of the J scanner is that always ensure that the tip is in contact with the surface, right? And if you really move this in this direction, you basically this tip runs over the the profile, right? Now, um, the top surface of this cantilever is basically reflecting. Okay, so when you shine a beam of light, it basically reflects. Okay, and this light falls onto something called a photodetector. Okay, there is a photodetector, and there are various detectors that are present here. This is called uh, position detector, and these are photo detectors because they detect light. So this light goes and falls on different detectors at different uh, depending on the topology. Let's say if it goes the tip goes here, then it may fall on some other detector, right? Let's say somewhere here it may fall, right? So basically uh, the purpose of the G scanner is to ensure that the tip remains contact with the surface. Then you basically move it from left to right or right to left. So this tip basically walks over this trajectory. And since depending on the topology, the reflected light will fall on different detectors. Depending on the profile, the detector on which the light is going to fall is going to be different. So basically, the detector is going to detect the position of the tip of the AFM, right? So that is how it is. So this is basically photodetector. They will convert this into electrical signal. So depending on which detector it falls, they will convert into equivalent signal, and they can basically on a output stage, they can reproduce this trajectory. Whatever you see on in here, the same thing is reproduced on the screen, right? So in such a system, uh, how can we talk about these different, uh, what is the sensor stage here? What is the transducer stage? What is the signal conditioning stage? What is the output stage? And what is the feedback control stage? So here you can see that the process input is basically the surface, right? Because that is what the we're trying to measure. And this cantilever is basically your sensor, right? This cantilever is basically the sensor because that is what is exposed to the process input. The cantilever is exposed to the profile, the surface. And the photodetector, the position detector is basically is the transducer because it converts the light energy into some kind of electrical signal. Okay. Now, when you take a photodetector, let's say there are a set of photodetectors. When light falls on this photodetector, typically light has a Gaussian profile, right? Something like that, right? Where the maximum intensity of light will be at the middle. So when this light falls on a particular detector, right, there is also, it picks here, but there is some stray signal which also falls on the detectors here and here, left and right. Okay. So here, the purpose of signal conditioning would be to ensure that these position detectors are appropriately identified, right? So let's say you have the signal, you basically chop the signal, right, which is falling on these side detectors here, and only consider the maximum intensity. That means you basically, let's say these are three detectors, you say that, okay, the light is falling on the second detector, not on 1 and 3. So this is the importance of signal conditioning in case of a system like atomic force microscope, right? You basically remove stray signal. The stray signal is removed using signal conditioning. Okay? Using some kind of thresholding, right? Now, once you have the topology, you know, typically you have a surface, right? And you are doing some measurement there, right? And once you are able to get some topology, let's say you already have some kind of idea that, okay, I mean, this should be the roughness and this should be the height, this should be the length. But if you get very erratic values, right? So you, your whatever signal you got, you must direct your feedback system. Your feedback system now does to direct the sensor to repeat the measurement, right? So the feedback uh, in this case of AFM could be to repeat the measurement. Let's say you are not happy with the measurement, or if you are happy with the measurement, you want to ensure that the profiles, if you measure once more, you are going to get the same thing. So you can, have your feedback system tell the sensor, the cantilever, to repeat the measurement. Or if you are done with the measurement, your feedback can tell the sensor to stop the measurement, right? So the feedback loop can ask for repeating, for stopping the measurement, or to move from one location, location A, to another location. right? It can, so you can tell, you relocate, and then start measuring again. Okay.
Sir, I have a doubt over there.
Yeah.
In the So my doubt is that the topology of the surface we have to measure, right, sir?
Yes.
That means
Yes.
that value is unknown to us in that way, and it is
Yeah. So
unknown to.
I'm saying that it depends on whether somebody else has already measured and told you, okay, you can expect something like this, and then let's say you should expect the surface roughness to be, let's say, 1 micron or 100 micron. But if you get let's say 1 millimeter, then you should get surprised that, okay, I mean, am I doing correct? So you can pick.
So it's a human feedback system in that way. Like
No, no, no. The
p-
feedback is basically you get the value on your screen, and you
comparing with the previous data that we have.
yeah, you can direct your measurement system that you repeat. So you just put some command, and we should ask the
I
sensor
got
to
it, sir.
repeat.
I got it, sir. Thank you.
But not necessarily always it will be human. There you may have a code which you can write to set, let's say, the expected value between some x and y, and if the value falls outside that range, you ask the system to repeat again, right?
Right, sir. We have to compare with some established value and then
Yeah, so it
direct.
can be automated as well.
Right, sir. Thank you.
Sir, I have a question.
Yeah.
So, signal conditioning effectively would only be like a filtering process, right? It's to ensure that the final input is being devoid of any noise or anything like that.
Yeah, so many times the signal that you get is a very low level and you are not able to really appreciate. So you can, in fact, do amplification sometime, or you are, in real systems are, sometimes the data is very noisy, right? So you need to put some thresholding to make sure that, the noise is filtered from the data, right? Noise is all extraneous effect that you do not have any control over, right? And we need to have it, it comes from experience, right? To how do you differentiate noise from data, right? So you need to do the appropriate thresholding through throw away noise without influencing data. And in fact, your analog to digital conversion also comes under signal conditioning study.
Okay. Thank you, sir.
Okay, so there are few things that I want to discuss, which is relevant to measurement. One is you need to have an experimental test plan. Okay, experimental plan. So, what do you mean by experimental test plan? You must know the kind of test that you should conduct, and so that you get the answer for the question you are uh, um, asking, right? So, for example, I mean, just from let's say from daily life, you say that, okay, what is the mileage of my new car, right? So, what are the variables that you would like to take? I mean, you have to take, let's say, how much distance it covers, or how much fuel that you had put. So that depends on further the accuracy of the odometer in the car, because you are going to rely on that. And so that's one variable. The second variable is that, okay, how accurately the fuel was filled, right? How accurately the tank was filled. So these two variables, the distance and the fuel volume consumption, have to be accurately put. And so this becomes two variables based on which you can actually answer the question how good is the new car in terms of mileage. Now there are of course other variables, right? For example, um, you talk about the driving condition, you talk about who is the driver, the weather, and there are various other variables which come in, right? So typically, when you want to mm, do, seek for answer for some of the question that you want to ask for your, let's say developmental work, you must have a test plan, right? So the first thing is you need to have identify all the parameters, right? So you need to have a parameter design plan. You need to have a parameter design plan, meaning you should know the objective of the test. Like as I said, what is the mileage of the new car? So you need to have the objective of the test, and you must identify the process variables. As I said, you need to know distance, you need to know the volume, the fuel consumption, and there may be some parameters that affect the particular test results. For example, as I said, the driving condition, the driver, weather, and so on, right? So, and you must ask yourself, what is that question I'm trying to answer, and what variables or parameters that affect my results. That becomes very important when you are talking about parameter design plan. The second thing is the system and tolerance design plan. System and tolerance design plan. Now, under system and tolerance design plan, you must select a measurement technique, right? For example, you want to measure pressure. Okay, what technique you want to use to measure pressure? And what is that particular equipment that you are trying to pick to measure? And what is the test procedure, right? What all you are going to do, right? Let's say you are using a manometer for pressure measurement, right? So that becomes your technique, right? I'm going to use manometric technique. Now, what is that particular equipment, right? I have U-tube manometer, inclined tube manometer, n number of different kinds of manometers. And what is the test procedure? What do I do exactly? How I fill the tube with some liquid, what kind of liquid I use, and what is the specific gravity of the liquid. So all these details should come under the test procedure. And in system and tolerance design plan, what is also important is how I do the measurements and how good the results need to be so that I get answer to my question, right? For example, if you are trying to measure the pressure, which is of the order of, let's say, 1 bar, and you are using an equipment which cannot really reach 1 bar, and then so it's of no use. Similarly, if you are trying to, let's say, differentiate a pressure between 3 Pascal to 5 Pascal, whether the equipment, the method, the procedure that you are you're using is sensitive enough to differentiate between 3 Pascal and 5 Pascal or not, right? So this all comes under system and tolerance design plan. And finally, you need to talk about data reduction design plan. So under data reduction design plan, you must plan to, once you got your data, you must plan to analyze the data and make the data presentable. You must, make suitable graphs and plots and so on, and make use of the data, So you must ask things like, how will I interpret my data, right? So do I need to, use a graph or a contour plot, or what kind of, representation I should make so that my interpretation would be easier, right? I get maximum out of what the data I have gotten. And how will I use the data to answer my question, right? Am I looking at certain kind of optimum value where, my y-axis is minimum or my y-axis is maximum, or am I looking at the slope of the curve? Okay, let's say I'm studying with respect to various different parameters. I'm looking at, okay, which parameter gives me the maximum slope. So what is that I am actually looking for from my data, right? So this is something that yeah, I need to really think about under the data reduction design plan. Okay, so these are some thoughts how you should actually plan for experiments. Um, and when you talk about experiments, you talk about variables, right? So um, when you make some measurement, you must identify all the variables. Okay, mainly the target variables. Let's say you are measuring temperature, you must take temperature as the dependent variable. But what does temperature depend on? Does it depend on thermal conductivity? Does it depend on how much heat flux that is coming? Does it depend on whether how fast the fluid is moving? So these become the independent variables, right, which control the dependent variables. So typically your target variable is a dependent variable, and your process is controlled through independent variables. For example, if I have, let's say I have a pipe and I am flowing some water through it, and I want to measure what is the pressure. So we know that the pressure difference delta P, if it is a circular pipe, I can write it as 128 into mu L divided by diameter to the power 4, 28 by pi into mu L diameter to the power 4 into the flow rate. That means if I am driving at flow rate Q and my diameter of the tube is D and the length of the tube is L, the viscosity of the fluid that I'm driving is mu, the dynamic viscosity, then the pressure difference should depend on these parameters, right? So delta P is basically the target variable, right? And your viscosity, length of the tube, diameter of the tube, the flow rate, they are all independent variables. So vary one of these, we are going to control this delta P. Okay. Of course, you need to be really, careful. Sometimes these independent variables, you assume that they are not, dependent on the other uh, uh, independent variables. But sometimes they may depend, right? For example, dynamic viscosity, if it is a Newtonian fluid, will not change with flow rate, right? But for a non-Newtonian fluid, the viscosity is a function of flow rate, right? So then strictly this is no longer an independent variable. It depends on another independent variable, right? So when you do certain experiments, depending on the complexity of your experiment, you have to make sure that your target variable is basically the dependent variable, what all parameters depend on, right? And when like situation arises where the one of the um, variables, um, uh, the independent variables as not really independent, it depends on other parameter, you must express the dependent variable in terms of independent variable, and you vary the independent variable. So you cannot really express in terms of mu. Mu must be expressed in terms of some constant and the independent variable. Make sure that you have all independent variable on the other side of the equation. Okay, so there are variables and then there are parameters. So what is the difference between variables and parameters? Variables are, we saw, right? There are dependent variable and independent variable. Parameters are basically functional grouping of variables. Okay, parameters are nothing but functional grouping of variables. For example, let's say in fluid mechanics, there is something called entrance length, right? When you flow through a tube, this boundary layer grow and the boundary layer merge, and beyond certain point, you have fully developed flow, right? Let's say this is entrance length, L subscript E. This entrance length is typically a function of the Reynolds number based on the diameter, right? And I hope all of you know what is Reynolds number. So this Reynolds number is, it comprises density, velocity, then some kind of length scale divided by dynamic viscosity. So you can see that here there are so many different variables, but they are grouped together to talk about a parameter, and this parameter actually characterizes um, some uh, uh, the variable that you are interested in. Let's say you are measuring entrance length. So you can, instead of talking about individual variables, you can group them together in terms of a parameter which characterizes this, right? As you know, a Reynolds number is used to characterize the type of flow, like whether it is laminar flow or turbulent flow, you can characterize using Reynolds number. So parameters are sort of a combination of different variables which can like generalize your understanding of a system, right? They are more broader than variables in general. Now, there's one more thing I wanted to talk in the context of the measurement. Uh, what is the difference between noise and interference?
Noise is constant, but interference is periodic, maybe,
Uh,
or occasional.
okay.
Noise can't
Any
be
other
constant.
thought?
Noise will not change the outcome or the data, whereas interference will change the outcome of the uh, sensor, maybe.
Okay, yeah.
Sir,
Sir, yeah, please go ahead.
Yeah,
Thank you.
please go ahead. I want to hear the thoughts about noise.
Sir, noise will affect the input. So unless the signal conditioning, like we spoke in the
Yeah.
previous parts, is conditioned to differentiate the noise and the inputs, and similarly the interference, the output will not necessarily change.
Okay, yeah.
The noise can be an external factor in the measurement,
Okay,
whereas the interference can be something from the system which is used for the measurement.
okay, yeah. These are all very nice thoughts.
Sir,
So
noise can be random also. Like what I mean to say is, it can go and come up in the measurement system at any random time. Whereas
okay,
interference will be more, I would say, scientific in that. What I mean to say is,
Yeah.
I'm not able. I don't have the words for that, but I hope
So
probably you
if
might
I
have
can,
got it.
yeah, if I
Yeah.
can try,
Yeah.
noise would be unintended, but rather interference would be intended.
Okay. Yeah. Yeah.
Just a
I mean,
thought.
yeah.
My thought is noise is we cannot assign a cause for noise, but for interference, it's something we plan or it is planned.
So, I mean, do you mean to say that interference is planned and it is predictable?
Maybe
No, sir.
this kind
No,
of
sorry.
periodic things happening during our measurements.
Maybe
Yes, sir, like interference is predictable completely.
Sir,
It
one more
can
thing
be
I want to tell that
quantified.
probably noise is from within the system, whereas interference can be what I mean to say influenced by other subsystems also, in in an intended way. Like for example,
Okay.
I'm measuring something, I'm measuring the EMF, but there is other source present over there which is
Yeah.
affecting
Yeah.
the signal. So
Yeah.
that could be interference.
Very good.
But noise is particularly intrinsic to the system actually in that way.
Yeah.
I
Which
agree
is
with
within the system.
Roshan. Yeah.
Sir, I would like to agree with what he said, but I work on cruise. I work on like cruise control. So there, noise is intrinsic, but it comes from an external source, like the road, for example.
Okay.
So noise cannot is both intrinsic and extrinsic in that sense, and it converges with interference because at the end it is having a say in how the input is being received by the system.
Okay. Okay.
Yeah.
Yeah.
Just
So
I'm
noise is at the input side, whereas the interference could be output side of the system.
Okay. Mm.
just my thoughts, sir. Like
Yeah,
interference.
yeah. I mean, these are very interesting thoughts. So, I mean, I would also share my thoughts about it. So, both noise and interference actually are, they affect, of course, the measure data, and the source is the extraneous variables. Okay, so there are various extraneous variables that affect measure data, and both are undesirable, both signal and both noise and interference. Noise basically would increase the scatter in the data, right? So typically, let's say you want to, I mean, just I'm giving a simple example. Let's say you want to have a signal with time, and let's say you wanted to get a nice sinusoidal curve, something like that. But in reality, you may get something like this. You may get something like this. Okay. So it increases the data scatter basically. Whereas if you talk about interference, interference is basically an undesirable but deterministic trends on the measured value. Okay. So if I let's say have this sinusoidal signal, but this is superimposed with another sinusoidal at a very different frequency, okay, along the signal path. So I may have, let's say, something like, you know, this, you know. So this could be a consequence of noise, whereas this could be a consequence of this is basically signal plus noise, and this could be signal plus interference. But good thing is, I think one of you said that this is predictable. I'm saying that this is deterministic, and it is on top of that the signal that you already have. For example, if you have an electrical instrument, you can have some noise coming from, either the other part of the system, or maybe there is some vibration. But if you have some let's say, some other power source or this AC power source, you can get a higher or lower order frequency getting superimposed with the existing signal and giving you something like that, right? And this may be something like that. Maybe there is a higher frequency over which this lower frequency is getting superimposed, and you are getting a effect of interference. But this is predictable because it is coming from certain source that is nearby your setup. All right, and so I mean, this is not just electrical signal, but you can get that in various other cases. For example, if you want to know let's say the effect of pressure on the boiling point of water, right? For example, let's say you make a plot, and this is time, and this is temperature, and you say that, okay, I mean, at 1 atmospheric pressure, the boiling point water should boil at 100 degrees centigrade, and this is 1 atmospheric pressure. Now, if I have a system, right, and I am trying to apply heat, and I am carefully measuring the boiling point, and I am also recording the pressure, right? If let's say this pressure is the pressure, let's say you are using maybe barometer, let's say, and this barometer is affected by interference, right? So you may get a curve which may look something like that, something like that. Okay, so you can say that your barometer is affected by interference. Okay, so whereas the noise in the data would be quite localized, and interference basically comes with the superposition with another, a signal of either higher or lower order signal. So I think time is up. We can stop here. But I think many of the input that I got is all towards in the right direction towards understanding noise and interference.
Thank you, sir. Thank you, sir.